Okay, let's start. And today I'm going to talk about refractive elements of eye, especially cornea, lens, and pupil, how it affects the total refractive elements of eye. I'm not going to talk about axial length and anything, but I'm going to talk about cornea, lens, and pupil. Okay, we are going to deep down into the optics of human eye, that optics of actually cornea, lens, and distances and all these things. Okay, the main refractive element of the main refractive element of the eye is cornea is definitely in crystalline lens, and one thing we don't have to forget it: distance between cornea and refractive lens, isn't it? It's important because what does it create? It creates the total power difference in total power, because if the distance between lens and cornea differs, total power of the whole eye differs. It's centrally important. And iris surfaces are aperture stuff. We know it. What is aperture stuff? And because of aperture stuff, light is controlled for the retina, but at the same time, aperture stuff helps to define in transpupil and exit pupil too. So transmission of light through the eye influenced by the transparency of ocular media, which also includes aqueous and vitreous. We know it. Okay. So cornea, the first interface is formed by the anterior corneal surface and air, and the average standard deviation is 7.82 plus minus this. This is the surface of corneal radius, and most model use this is, isn't it, 7.7? So for corneal front surface, we always think 7.7 is the average. The second interface is formed by the posterior corneal surface with aqueous humor, and the average radius of and standard deviation is 6.8. We always consider front surface 7.7 mm, back surface 6.8 mm, isn't it? As I have already discussed in the previous video, which is schematic eye. Okay. So here in this picture, I want to tell you the best thing that you just understand. You have to understand. Front surface, told you is 7.7, isn't it? Back surface, I have told you 6.8 mm. Okay, just think about it. Front surface, what is the power of front? Sorry, power of a surface, n dash minus n divided by r, isn't it? So n dash minus n and r both matters. The more radius curvature, the lesser the radius curvature, more the power, isn't it? Power is inversely proportional to radius curvature, but power is directly proportional to the difference in index. So see, I want to tell you one thing. Though the back surface has a radius of curvature, smaller radius of curvature, isn't it? 6.8. Though back surface has a smaller radius of curvature, back surface has a smaller radius of curvature, but back surface has less power. For example, front surface has 1.376 minus 1 divided by 7.7 divided by 1000, isn't it? So this is the actual power of front surface, but back surface is really crucial. 1.336 minus 1.376 divided by 6.8 divided by 1000, isn't it? So difference between the index of cornea and aqueous is so small, that's why back surface becomes minus 6 power. Okay, isn't it? See, what is the anterior corneal surface has power of 49 and posterior surface of power of 6, isn't it? It's only because the index difference between these two things, aqueous and cornea, is so less, and index difference between cornea and air is high. That's why. Otherwise, if it is not the case, so food for the thought. What would be the cornea power if cornea were surrounded by air in both sides? See, if both sides is cornea surrounded by the air, then posterior side power would be 55.29, and just consider it 49 plus minus 55.29. What would be the power of the cornea? The power of the cornea would be around 6 diopter in negative. What we are considering now, cornea power 43 diopter and plus 43 diopter. Why this happens? Okay, this is crucial question that I want to ask you. Why this happen? Instead of air, here is 1.336. So instead of 55, this power reduces down to 6 diopter because posterior surface is covered by the aqueous. That's why plus 49 plus minus 6 is 43, and all our school teaches us it's 43 diopter cornea. But if it's because of the aqueous humor, because posterior surface is surrounded by the aqueous humor, otherwise it is not possible at all. See, I want to tell you one thing that is very, very fascinating, and I think you will enjoy this thing. So let's take example. This is front surface of the cornea, and let's take an example. This is back surface of the cornea, isn't it? So let's take an example. Cornea. See, I'll show you here. Okay, this is the cornea, isn't it? Cornea has thick periphery and thin center, isn't it? Center has 450 micrometer, periphery 6 micrometer, and it is a meniscus shape. Okay, it is a meniscus shape. I want to ask you one question: if it is possible or not having meniscus shape and center is thin and this lens is plus, is it possible? Not at all. You cannot see this type of lens. Whenever you are talking about a lens with a center thin, periphery thick, with meniscus shape, it must be negative lens. But the posterior surface is surrounded by the aqueous, and that's why posterior surface power from 55 reduces down to directly 6 diopter. That's why we consider cornea as a positive lens. Otherwise, even anatomy of the cornea and the shape of the cornea is not a positive lens shape, it's a negative lens shape. So you have to understand this paradox. Okay, and the distribution of equivalent power of human eye in healthy population, so maximum power falls under around 43 diopter. Cornea, if you have to close your eye and tell one power for the cornea, it is 43 diopter, but it's not like that. So in it's normally distributed, and power may range from 40 to 48 almost. Okay, so equivalent power of the cornea. What is the equivalent power of the cornea? If we consider that thickness matters, then we have already discussed equivalent power of the formula. Equivalent power is f1 plus f2 minus t by n f1 into f2, isn't it? Equivalent power of the cornea. Using a standard value, third connective term introduced the Goldstein formula only contributes this power to the total. See, 0.11. Is it that significant? Not at all. That's why we do not consider cornea as a, we do not use this equivalent power formula. Okay. So corneal asphericity and toricity is centrally important. The corneal asphericity is only approximation of the perfect sphere. This deviation from sphere is called asphericity, isn't it? Whenever the shape is deviate from sphere, it is called a sphere. So sphericity also varies in different meridian and can also be demonstrated in corneal topography. Among the rotationally symmetrical shape, sphere, spheroid, ellipsoid, and paraboloid, hyperboloid, and their intersection on the two dimensional is circle, ellipse, parabola, and hyperbola. Only sphere and circle has zero sphericity. See, if we call it in 3D, it's called sphere. If we call it in 2D, it called in circle. Okay, if you call ellipsoid in 3D, in 2D it's called ellipse. If you call paraboloid in 3D, in 2D you call parabola. If you call hyperboloid in 3D, in 2D you call hyperbola. It's centrally important what you call it. Okay, for the cornea, we usually use asphericity index, which is q value, or conical parameter shape factor, which is p value. This is very important in case of orthokeratology. Eccentricity value, which is e, and we can convert to each other. q is equal to minus e square, p is equal to 1 plus q, and p is equal to 1 minus e square. So normally for ideal sphere q is 0, hyperboloid q is less than minus 1, and paraboloid q is exactly at minus 1. So you have to understand these things, okay? Q is sphere is 0. In case of cornea, cornea is paraboloid, and paraboloid cornea falls under around here, isn't it? So this is the picture. You can see this picture. Okay, hyperboloid means greater than 1. So prolate sphericity is the natural state of human eye. Just remember this. It will always come in the MCQs. Human eye has which type of sphericity, and option is prolate, oblate, parabola, hyperbola. It's always prolate. Okay. So which means flatter cornea at the periphery. So basically cornea is steeper at the center, and as you move periphery, it becomes flatter and flatter, isn't it? So that type of surface is known as prolate. So flatter cornea at the periphery and steeper at the center, and that type of surface shape is prolate. Okay. Typically, central anterior cornea is about 3 diopter steeper than periphery. I think it's more than 3, but it's completely okay. Sphericity usually has different value away from the center. Usually sphericity is always not one value, but we have to wrap as one value, but it is different from center to periphery. So visually significant area of optical zone, which approximately corneal area, which is same extent as the entrance pupil, which is very important. Visually significant is usually 2 to 3 area, but it's usually extend to entrance pupil. Typically, larger the optical zone, greater the sphericity as it deviates from the spherical. So we consider 2 to 3 zone is spherical, even not aspherical in case of cornea. But yes, if you take larger optical zone, the greater the sphericity. Okay. So for 6 optical zone, 3 away from the center, the average corneal sphericity is this. It will come in your MCQ always. What is the sphericity of cornea? So you must remember that the sphericity of cornea is approximately 0.3. Okay, for 8 zone sphericity is 0.51, but if it comes in exam, it will always approximately 0.3, or sometimes it's 0.26 or around whatever. But you remember this point: cornea sphericity is approximately q is equal to minus 0.3. Okay. So optical importance of sphericity is spherical aberration, isn't it? I have already discussed it. With we have cornea as prolate, which helps to reduce the positive spherical aberration. The average eye has 0.5 root mean square positive longitudinal spherical aberration. The interesting aspect of the contribution of spherical aberration cornea and from the lens have opposite sign, which is very interesting. Cornea has spherical aberration in a positive, and lens has spherical aberration in a negative sign, so that's why they cancel each other. Partially, at least corneal spherical aberration compensate for lenticular spherical aberration, leading to overall reduction in spherical aberration. That's the beauty of nature, isn't it? So cornea has one positive spherical aberration and lens has negative spherical aberration, and both cancel each other. That's why total spherical aberration, when image reaches towards the retina, it's reduced in overall. So theoretically, cornea q value can be average is 0.53. So if we want to eliminate the longitudinal spherical aberration, then q value must be minus 0.53. This is just if q value is 0, then longitudinal spherical aberration is dropped to 0. This is just a theoretical aspect. So average cornea, you will say minus 0.27 or minus 0.3, whatever. Okay. So central zone posterior corneal sphericity has about, this is posterior, not anterior. Anterior is to say, okay. Our biggest posterior surface has negative power, and the difference of refractive index between cornea and aqueous is very small. So contribution of spherical aberration is very small because the surface has power. Posterior surface has smaller power, very small as compared to front surface is 49 posterior surface is 6. So this power has a contribution of spherical aberration very less, because the power itself has very less in case of posterior surface, but anterior surface is huge power, isn't it? That's why anterior surface sphericity matters more. So corneal sphericity, in final touch, the cornea is not an ideally sphere surface, it's very important, but aspheric. It is stiffer at the center and flatter at the periphery. That's why it's called prolate, isn't it? So sphericity can be expressed mathematically by the parameter of Q value, or sometimes shape factor. Okay, sometimes eccentricity. You have to know the formulas, all the formulas converting one another. Sphericity compensate for high order aberration such as spherical aberration, and we have discussed already corneal spherical aberration and lens spherical aberration. Corneal sphericity must be in design with a profile of laser refractive surgery or the selection of contact lens. It's very important. Even the sphericity helps diagnosis of keratoconus and management of keratoconus. It's important. Okay. Distribution of Q value in healthy population. See, normally Q value falls under this point around 2.7 minus 2.7. So otherwise we have other options too. So sphericity, the difference in curvature between center and periphery. Typically, cornea is steeper at the center and leads to spherical aberration. Okay. For toricity, the difference in curvature between the principal meridian. Typically, cornea is steeper at the vertical meridian and relates to with the rule astigmatism, isn't it? So sphericity and toricity, don't confuse with it. Toricity means it's a toric, it's cylinder. Sphericity means aspheric, which is shape of surface, prolate, hyperbola, parabola. It means with the rule astigmatism, against the rule astigmatism, and all these things. Toricity means the cylindrical power. The two meridian has different power. Sphericity means the surface shape, which is prolate, as a circle, parabola, hyperbola, and all these things. Okay. So let's come to the crystalline lens. Crystalline lens convex has a center of thickness around 3.5 to 3.8 in adult. Its optical interference are the anterior surface with a radius of curvature of this, and posterior surface with radius of curvature is this. See, the average refractive index of the lens is this, but we know that cortex has one refractive index, which is one, nucleus has one refractive index, which is this, isn't it? So this is for cortex, this is for nucleus. So see, it's very simple. Posterior surface has curvature of -6, anterior surface has curvature of +10. So that's why power of posterior surface is higher and power of anterior surface is lower, isn't it? It's very simple. So it's simple to understand this concept, okay? And the lens is surrounded by 1.33 refractive index by both surfaces, okay? And another point, that if you have to pick one number, the lens must have highest power of 21 diopter. Okay, so this is on an average distribution of optical power of healthy population. So lenticular toricity and sphericity. Toricity, the lenticular optical power varies along the different meridian. Typically, along the largest optical power lens along the horizontal meridian. So lens itself is not a spherical. Lens can sometimes show toricity, and not naturally it has a little bit toricity, but it's not that much huge. Sphericity, the sphericity of the lens in a young population up to 40 years has the same magnitude and opposite sign compared to the cornea, which is negative spheric, uh, which is negative sphericity, which contributes to reduced ocular spherical aberration. And lenticular sphericity aberration degrades changes to 0 at the age of 40 when it becomes positive. So after the 40, then spherical aberration becomes positive. You have to understand this. Clinical relevance. The clinical relevance of the above important in the selection of sphericity intraocular lens cataract surgery, achieving the corneal sphericity by laser correction procedure. So IOL today and such as tennis. So we use IOL of negative spherical aberration to neutralize the cornea's spherical aberration, so that total ocular aberration becomes 0. And this is not available in like India and Nepal, but I think I don't know about India, but it's not practicing currently in Nepal, but I hope it will be in future. So basically the aim is to maintain the corneal sphericity. The custom design ablation aims to preserve the corneal sphericity and object being preserve total ocular spherical aberration. So it's very important to understand why we want the total spherical aberration into the check with lens and the cornea, because if you reduce this total spherical aberration to zero, it will create what? It will create reduction of depth of focus too. That's why we don't want exactly at zero total spherical aberration, but within the limit, so that our visual system work well. Okay. What is the lens paradox? It's just a topic I introduced here. Just let's discuss in very gross. Okay, the lens paradox. There are substantial evidence that the aging lens gradually changes itself. The anterior surface becomes steeper with the age, and the radius of the anterior surface decreases from 15 mm to 8 mm between the age to 20 to 18. The smaller effect takes place that the posterior surface, the posterior lens surface reduces this to this. And this law particularly, it is easy to decide the lens curvature changes and increases the lenticular power and tendency towards the myopia. Since, however, that is clinically observed between 30 to 80, it is not myopic shift but hyperopic shift. This is the lens paradox. Hypothesis is a reduce in refractive index, change in lenticular sphericity, and aging in the lens, because since from aging lens surface curved more, and that's why it should create myopia, but in reality with age people are getting hyperopic, and that's the paradox. Okay, so I'm not trying to discuss this a lot because it's a lot older uh, paper. So so this is why graded refractive index of lens is so important. If fixed refractive index of the lens, then it will create large spherical aberration. But naturally, refractive index of the lens is graded. That's why spherical aberration is minimized. This is one of the advantages why we have graded refractive index in our lenses. So anterior chamber depth. So anterior chamber depth solves the space between lens and the cornea. So the distance affect the optical power of the eye and indicate the way of means of third term in the Goldstein. Third term means f1 plus f2 minus t divided by n f1 into f2. This is third term. Okay. So as the optical power changes, okay, optical power changes. Change in the optical power dependent variable. Various shift means spacing between the lens and external lens. If the power between optical power changes, so if anterior chamber depth increases, what happens? So see, I'll show you. 43 plus 19 minus t by n, 43 into 19, sorry, 43 into 19, this is positive, sorry, 43, this is positive, this is positive, t is always positive, n is always positive. If t increases, all the thing here increases, isn't it? If t divided by n, 43 into 19, this is positive, this is positive, this is positive, and this is positive. If this increases, t getting increases, the more and more power increases, the total ocular power decreases. That's why it becomes hyperopic. So total optical power decreases and it becomes hyperopic as the distance between cornea and lens increases. So that's why distance between cornea and lens increases, people become hyperopic because total power decreases. Because we know that, isn't 60 means emmetropic, then 58 means hyperopic, isn't it? 64 means myopic. Total power I is 60 is emmetropic, then 58 is hyperopic, 64 is myopic. That's what the concept. So total power of the whole eye decreases as the cornea and lens distance get increasing. Okay, that's the concept. So aperture, optical aperture, which means the uh, pupil. If pupil is dilated, then all the light comes from this fish and image is getting blurred. But if pupil is small, then image is sharp, isn't it? That's very important. So iris optics, Iris is aperture stop. Entrance pupil is image of the anatomical iris formed by cornea, because as I have discussed, whenever there is aperture stop, the aperture stop image of aperture is formed by anything in front of the that aperture stop, and image of a aperture stop made by anything behind that aperture stop is exit pupil, isn't it? It's entrance pupil. So entrance pupil, anatomical cornea, which is optical element of preceding pupil, so made by cornea. So looking at the eye, we see the anatomical pupil, but but image through the cornea, which is then entrance pupil. So normally entrance pupil is approximately 13% larger and around 0.6 mm closer to the cornea as compared to actual pupil. So clinical note: microscope, telescope, and slit lamps or surgical scopes, the exit pupil of the optical instrument must be matched to the entrance pupil of the eye. So it's very important. Okay. So entrance pupil affect the optical zone, depth of field, and optical aberration, isn't it? When selecting the contact lens or planning laser refractive surgery, the optical zone must cover the diameter of entrance pupil. That's the concept. That's why we always measure uh, contact lens back optic zone diameter, front optic zone diameter. In case of refractive surgery, we always do ablation diameter, and we always try to do the pupillography. Why it is important? Because we know if pupillography shows the entrance pupil, pupil itself is so large in dark condition, then we have to understand that it needs a larger back optic zone diameter and or larger ablation diameter and all these things. Okay, a smaller pupil, we have discussed already, increase the depth of field and depth of focus, isn't it? Why? Because it reduces the geometrical blur. Larger pupil reduces the depth of focus and depth of field, because depth of focus is always inversely proportional to pupil size or aperture stop size. Okay, exit pupil is the image of pupil via the lens, because by back side of the lens, back side of the pupil, in image space. Definitely it is a virtual image usually located in front of the pupil and somewhat larger than the pupil and lesser degree than the entrance pupil. It's almost 3% larger than the actual pupil. Okay, this is what the basic of all optical element of the eye. Let me summarize it for you. Cornea, we know front surface and back surface. Why back surface reduces from 55 to 6 diopter, minus 6 diopter? Because of the aqueous humor surrounded. Lens and the space between lens, these all the things, and asphericity, it's all these things are central important. Okay, okay, these are my references. Great book, history start, good book, and I have also taken some portion from this book, and my favorite book from Professor Dr. George S. Melis. Okay, bis dann, tschüss.